Hello everybody, my name is Advika from UNT and this is my project on the effect of collision cascade on nanoscale cracks in metals. First, it is important to know the motivation behind this project. Nanoscale cracks are inadvertently introduced in materials during servicing and or processing, no matter how much we don't want them to happen. They are for the most part inevitable. Now imagine a material that is subjected to radiation effects and also has pre-existing nanocracks within it. What happens to these cracks then? Do the atoms displaced by high-energy neutrons and heavy ions from the radiation close the crack, or do they help in growing the crack more? In the first simulation that I ran, we found the crack to close. Then, we decided to vary the distances of the primary knock-on atom, or PKA, and see at what point the crack is not affected by the cascade. Okay, I'm sure there's lots of questions from the terms that I'm just throwing around at this time, but I'll be breaking it all down for you in the next two slides. Keep in mind that this project employs atomistic simulations. These are extremely small scale, and I make cracks by just taking off 2 layers of atoms. Now, I will be talking about the building blocks of this project. First off, we need some system to work on. For that, we chose the metal nickel, which has an FCC packing order. All of the images that you will see in these slides have been rendered using the visualization software OREU. The green particles indicate FCC packing of atoms. Next, we introduced a disc-shaped crack in the system. We specifically chose its diameter to be 50 angstroms and its height to be at 4 angstroms, or 0.4 nanometers, after taking off 2 layers of atoms. The last thing that we need to start our collision cascade is the PKA. This is just a single atom that we chose from within the system and gave it a kinetic energy of 10 kiloelectron volts and a certain direction. So, I've been using the term cascade for a while now. What would a collision cascade exactly be? It's actually something that metals experience whenever it's subjected to radiation. Radiation is composed of high-energy neutrons and heavy ions. We also know that a metal has a very ordered structure. So when these high-energy neutrons and heavy ions hit the metal and knock on some atoms, their high energy gets transferred to these atoms, which further want to dissipate all that energy and reach their stable state by displacing other atoms in their way. This process continues until all the atoms in the state that have been affected by it reach their minimum state. And the name given to this is collision cascade, because these collisions keep coming one after the other. I have rendered the movie that you see here using OREU from the LAMS dump files. LAMS is a molecular dynamics simulator. We only see white atoms here because these are the ones that have been displaced. I have suppressed the atoms that were in their perfect FCC ordering, indicated by the color green, so we can better see the collision cascade process. The first test showed an interesting result. We chose a system size about 3 times or more the crack size, and the PKA was chosen to be quite close to the crack along the horizontal direction. What I have here is a sliced view of the first test run. During the simulation, we see clusters of distorted regions forming around the crack, and then at the end of 15 picoseconds, we find the crack to be closed. And there is also formation of stacking faults indicated by the red HCP atoms. As a side note, I have used the OREU modifier Common Neighbor Analysis to group these atoms into categories of different ordering types, like FCC, HCP, BCC, and so on. How does this modifier work? It does it by looking at the local ordering around the atom of interest. So after the results from the first test, we decided to basically blow up the system along the Z direction and make its length 5 times the original length. We did this so we could choose PKA at greater distances and determine at what point the crack doesn't close up or the resulting cascade from the process does not affect the crack. On this slide, I have some results on the state of the cracks after each simulation by varying the PKA distances from the crack along the vertical direction. I have a schematic of how that was done on the next slide, but for now, we can see that the crack essentially closes up until 50 angstroms, but at 100 angstroms, the crack is not affected at all, and it's just like how we see it in its initial state. I only chose these points of data for ease of presentation. On this slide, and in the next couple slides, I have some quantitative information. Here, I have a plot of the number of surface atoms of the crack as a function of the vertical PKA distances in angstroms. To the right, I have a schematic of what both these quantities are. What we see here is actually how the different PKAs were positioned with respect to the crack at distances of 10, 20, 50, and 100 angstroms vertically along the z direction, although they weren't outside the box like we see here, but within it. And to the left, we see the state of the crack surface atoms for each of these tests. It was observed that the number of surface atoms decreased with increasing distances until 50 angstroms, and at 100 angstroms, it remains unaffected. This was interesting because it is expected that with increasing distances, the interaction between the cascade and the crack becomes less and less. So I sort of expected the crack surface atoms to increase with increasing distances, and found the contrary until the cutoff, that is 50 angstroms. So I decided to do a little more digging and quantify something else. On this slide, I have 4 pictures with red squares around it. Those are the snapshots of the distorted regions at the end of 15 picoseconds for each test run. I found that with increasing PKA distances, more and more stacking is favorable because at lower distances, it's very easy for the crack to be filled by the displaced atoms, so there is not as much stacking. The plot here shows the height of these distorted regions or stacking as a function of the vertical PKA distances. For simplicity, I have ignored the smaller clusters surrounding the bigger region. I have compared this plot to the plot of the number of crack surface atoms to show the inverse relation. To conclude my project so far, we can say that the degree to which the crack heals or closes depends on the PKA distances. Further away the PKA is from the crack, the less likely it is to heal. This was a very exciting project for me to work on, and it has a lot of scope in the future. For instance, we can vary different parameters, like increase the energy, make the crack bigger, try out different PKA directions, and also maybe try to do this in a real-world experiment. Due to the time constraint, I wasn't able to look into the mechanisms at play here in detail, so that's another thing to look at in the future. I would like to express my gratitude to the Texas A&M O-REU program for summer 2020 and the TAMO HPRC resources that enabled me to work on this project. Most of all, I would like to thank Dr. Michael Demkovich for taking me under his wing and mentoring me with his expertise. I would also like to thank my auxiliary mentor, Dr. Peng Chen, for helping me with technical difficulties and for solving any queries that I had. Also, this wouldn't have been possible without the fellow OREU participants and Mac, Christopher, and Zach for their advice. Thank you.